Hi math students, it's Miss Carol, and we are now working on Unit 4 projects for Algebra 1B. You didn't have any project questions for Lesson 16, and you won't have any for Lesson 18. So we've only got Lesson 17, 19, and 20 for this unit. For Lesson 17, we have got 6 questions, and we're dealing with exponential growth and exponential decay. So here's our background. The change in animal populations from year to year can often be modeled using exponential growth and decay functions. The following examples discuss endangered bat populations in the U.S., which are incredibly important to our environment, as they pollinate plants and control insect populations. Use your knowledge of writing exponential functions to model these populations in a wild preserve. Okay, so question 1. Is the Mexican long-tongued bat population is an endangered species, which decreases at a rate of 3.5% per year in a wildlife preserve that currently has 80 of them. Okay, so the population is going down, and we can pretty much assume this is kind of a gimme question because we're seeing that decrease, that we're dealing with exponential decay. All right, but let's think about this, that if in year 1 there's 80 and it goes down by 3.5%, so let me figure out what that would be. 3.5. Okay, so in year 2, there's only going to be 77 of those bats, and then it's going to still go down 3.5% of that. So the 3.5% is staying the same. So it's kind of scary. You would think that maybe as the numbers go down, that they would start to go down slower, but they're going down at that 3.5% per year of that total, which is why it's an exponential decay. All right. And I guess something to think about, 3.5% of 77 is going to be less than 3.5% of 80. And so there will be fewer that decay in that 3rd year and fewer that decay in the 4th year, but it's still going down by that much a year. So hopefully that makes sense. All right, so this is kind of the math that I just did. Which functions correctly model the population of the endangered species after X number of years? So let me get my pen going. And so if we start out with 80, and it goes, let's say it stayed the same, so we could just multiply 80 by 1, and that's if it stayed the same, but it's not staying the same. So we're going to say 80 minus that 80 times 1 minus that 0.035, okay? And then that's happening every year, so our X is going to represent the number of years that's happening, okay? So that's one way, all right? And then the other kind of way to look at this is exactly the same thing, but we're going to simplify that. So it's going to be 80 times 0.965 to the X. 1 minus 0.035 is 0.965. Okay, so both of those are going to work because essentially they are the same thing. So that and that. Okay, hopefully that makes sense based on what you've learned. All right, so that's our exponential decay. Hopefully you can imagine that the next one might be an exponential growth. Wildlife preserve specialists have developed a plan to rebuild the population of northern long-eared bat by 2% each year. There are currently 150 of the animals in the preserve. Okay, so this then would be modeled by exponential growth if they want to increase it by 2% per year. Because if they increase it by 2%, if they start out with 150, and then in year one, we would multiply that by 1.02. And so in year one, there'd be 153, okay, after year one. After year two, you'd multiply 153 by 1.02. And you'd go up to 156. And so 2% of an ever increasing number is going to be bigger. And so it's as your base number, that 150, as that grows, your 2% of that is going to get bigger and bigger and bigger. So if you can imagine this like a bank account, if your principal stayed the same and you only grew off that same principal every year, it wouldn't be very much, it wouldn't be worth doing a bank account. But if you get a growth and then that principal grows and you get a percentage off of that, and then that principal grows some more and you can take that same percentage off of that. That's why doing a savings account or investing, doing a retirement account of any sort makes a lot of sense compared to just stuffing cash underneath your mattress. So this one is exponential growth. All right. Okay, so the formula, I kind of gave that away, is going to be that 150 times 1 plus 0.02 to the x power, okay? And if we combine these, it's that one, okay? Hopefully that makes sense. And that x power represents the number of years that they've been working on increasing that population. Okay, 2 more questions. How did you use the keywords in the problems to determine the type of functions needed to model the scenarios? So I think we can do this really easily. I think we should just go ahead and type in here. This is all I'm looking for. The keyword of rebuild indicated to me that we were dealing with growth. And the keyword of decrease for the first one indicated to me that we were dealing with decay. You don't really need to put anything more than that. It's okay to have a very clear and concise answer there. So explain how to determine the % rate of change for an exponential function. So for growth, we would have 1 plus % change. Okay, so for that 2% growth, we had 1.02 because 2% is 0.02 in a decimal, so we had 1.02 for growth. And for decay, we have 1 minus % change. So when you're looking at functions and trying to determine if they're growth or decay, if that base is greater than 1, it's going to be a growth function. And if that base is less than 1, it's going to be a decay function. Okay? Hopefully that makes sense. And that's really all I am looking for here. So thank you so much for joining me. This was short and sweet, and I will be back, not for lesson 18, but for lesson 19 and lesson 20. Thanks.